Hi, and welcome back to Printing Cities. It's been a little while, but finally I have 15 large San Francisco tiles ready to go to finish up, mount up on the wall and make into an art piece. And so let's talk about how I got here. Let's go through things like the fabrication processes, the different options I've had, the pros and cons of each, and why I finally chose 3D printing. 3D printing itself and some of the challenges that particular method faces with this kind of project, and finally taking those 3D prints and how to finish them and place them onto a single mount to make a single thing to put on the wall. But first up, let's talk fabrication methods. When I started this project back with the London map, I only had one particular method available to me, 3D printing. Since then, I've gained access to a number of different kinds of machines and methods to make things, from a milling machine and a CNC router to a laser cutter and a water cutter, and even things like mold making equipment. And so I want to talk through these different approaches to fabricating and making things like these city tiles, and the different pros and cons they have with these kinds of approaches. So first off, let's talk additive manufacturing. That is, starting with nothing and adding material to make a thing out of it. And in particular, let's talk 3D printing. Now, 3D printing is very popular these days. A lot of recent advances in technology and the way we do things has allowed us to make 3D printers smaller and cheaper than ever, and you can have them in the home or in the office. They're a lot more accessible and cheap and affordable than many of the bigger, more difficult manufacturing methods. And so it's an obvious first choice to turn to for a hobby project like this. Now, there are some disadvantages to 3D printing. In particular, the things that it can make are often reduced in strength. Because you're making a thing out of layers, you're literally making it and building it a layer at a time, the end product ends up being sort of very brittle and easy to shear off along those layers. And you're also limited with the materials you can use. Now, I have what are called FDM printers, that's fused deposition modeling. That's a fancy term for it melts plastic onto itself. But this means you can only work with certain kinds of plastic. And in this case, I have a printer that can do ABS, PLA, and nylon. Now, there's a decent range of plastics, but they each have sort of particular problems with things like attracting lots of water or bubbling up or being a bit easy to melt at high temperatures. And so the end results in 3D printing are often decent, but they're not often long lasting. And so that's one of the considerations to have when you're making things out of it. The other main method is subtractive manufacturing, and in particular CNC milling. What this is taking a big block of plastic or metal and a machine that takes a series of different size and shape bits and runs them through, taking away material in certain patterns and shapes to leave you with what you wanted in the end. A milling machine does have advantages over its 3D printer counterparts. For one, it's much more accurate. It's often made to a fraction of a millimeter accuracy. And on the other hand, you also are taking away things from a solid block of material, which means the end result has none of those layering issues. It's a single solid block of wood or plastic or metal, and it's going to be much harder to break things off. The downside is, of course, the geometry. When you mill something, you have to be able to have a shape where the machine can take the milling bits and get into the places where it needs to remove material. That means if you have lots of long, narrow, shallow valleys, like say between buildings in a city map, you're going to have real problems with the milling machine having to get a tiny, long, thin bit through that narrow valley without breaking. It's possible, but you have to go slowly, and I mean very slowly. The tiles I'm sitting in front of would take between 15 and 30 hours each to mill out of a solid piece of metal. That's a long time for a machine that I only have access to in 4-hour blocks. And so practicalities mean that even if a milled result would be much more beautiful, much stronger and harder wearing, I just don't have the equipment or the access to do that with this project right now. Now, there is a third option, and it comes with a bit of a twist. Additive manufacturing, like 3D printing, can make very decent looking positives. But what you can do is take those positives and use molding and casting to make a mold of the original positive and then cast a new material into that to make a much more solid version. In particular, cast materials, because they're casting all at one time rather than being built in layers like a 3D printer, end up being much more solid. And you have a wide range of materials to choose from. You can have clear resins or solid resins or even flexible rubber-based or silicone-based materials. There is a problem though with casting and molding, and that is the mold making process itself. Molds are very tricky to design. Not only do you need to make a mold so that the resin or plastic can flow into every tiny detail and crevice, but also once it's done that and set, so you can get the mold out again. It can be very easy to make a mold that looks good initially, but you try and pour material into it and set it and it won't pull out properly, or you'll have bubbles all over it, or the tiny details won't be done properly. And in particular, I've tried to make molds of some of these tiles. I've done some test runs with urethane and silicone molds, and the results aren't terrible, but getting the fine detail required for these models is difficult. I suspect with a vacuum chamber and a pressure chamber, I could probably achieve decent results. But again, this is still an introductory project kind of thing. But 3D printing in the end has proved the most reliable way for me to make these city tiles with the skills and tools I have access to. There are other projects I've done on the milling machines and casting, and I'll introduce those in later videos. But for now, let's go and look at the 3D printers and let me explain some of the problems and difficulties I've had and some of the ways I've tried to solve them. So, let's talk about 3D printers and the different types they come in, and in particular, how they deposit materials and make up an object. Now, what I have here are both FDM printers. What that means is they take a big spool of plastic, like this one, and pass it through what's called a hot end to melt the plastic, like this one. Once it's gone through the hot end, the plastic's molten into layers and the object's built up layer by layer to make the final result. There are other kinds of 3D printers that use things like lasers to fuse material or ultraviolet light to cure resins in place in a liquid bath, but FDM printers are generally the most easily accessible kind of printer and don't need much maintenance, so they're generally a good choice for someone working at home like I am. Now, within FDM printers, there's a couple of different types of movement and that affects how they print. The most standard type is a Cartesian printer, and that's what I have here. A Cartesian printer moves its print head through X, Y, and Z axes that are perpendicular to each other. It's pretty simple. It's pretty much the first thing you might think of when you think of the challenge, how do I move a print head through 3D space? And that means it's easy to understand and easy to program for. The second and slightly weirder kind of printer is a delta printer, which is what one of these is. A delta printer still has three axes, X, Y, and Z, but those axes actually stand up parallel to each other. And the combination of movements of these axes with these lever arms mean the printhead moves around in 3D space based on the way the different axes move. Now, you might wonder why you'd have a delta printer when a Cartesian seems much easier and simpler to program for. And the key thing is there's a trade-off. The delta printer can move a lot faster. The way the delta arms are arranged means that the effector here can move around much more quickly and accurately compared to a Cartesian printer, because you can use all three axes at once. The trade-off is, however, the movement calculations. Deltas have to perform incredibly complex calculations involving calculus and trigonometry to work out where exactly in space the head's going to be as they move the three belts on these different posts up and down. And that means that the accuracy is very difficult to get. In particular, often delta printers, as you get further away from the center, get less and less accurate. And so you really have a trade-off between speed and accuracy for these two printers. Now, in my case, the Rostock here, which is the Delta printer, was the first 3D printer I owned, and the 3D printer I did my London model on. The London model, as you may have noticed, is made out of small 7.5 centimetre tiles, and that means they stay pretty much within the safe area on the printer, and they kept pretty accurate. Even then, the tiles are very slightly rhomboid. There's a lot of different parameters to tweak on a printer like this to make it perfectly accurate, and even a few tenths of a degree out on the angle of the different towers relative to each other can cause differences like that. And so it worked all right, but the tiles still have a slight visible edge to them when they're tiled together. Now, I tried to make some of the San Francisco tiles on this printer, and of course, they're bigger. They're 15 by 15 centimeters. What that means is they fill up pretty much most of the printable bed area on this machine. And that means you're really pushing the accuracy limits of the printer. What I was finding was that the machine's Z homing, that is making sure it's exactly the right height to print, was getting further and further away from the bed as they got further away from the center. And this meant my tiles were peeling at the edges or coming unstuck or generally being uneven. So I spent some time trying to tweak parameters and tune the printer, and in the end I got pretty decent results. It wasn't perfect, but the Z accuracy was pretty good across the whole bed, and generally, as long as the first few layers stuck down, the print would go pretty well. That's when I came across the second issue, which is oozing and stringing. Now, when a printer prints, it has to print layer by layer. It can't do one thing, then go back down and do a different thing. What that means is, if you've got 2, 3, 4, or in the case of cities, many small objects, it has to go between the objects each layer. And what it often does is it will drag a small trail of plastic between the objects to cause tiny strings. You can see an example here on this 3D print. This has two separate sections, And between them, as the printhead has moved for each layer, you get these tiny fibrous strings here that show you that there's been a little bit of oozing at the printhead. Now, this is related to the other kind of difference between these two printers, the kind of extrusion. Remember, they feed from a big spool of plastic like this. What that means is something has to take the plastic and push it through the printhead. Now, in a case of this, a direct drive extruder, the extruder motor is directly on top of the printhead. And so it literally just takes in the plastic, there's a small cog in here that rotates and pushes it through directly into the hot melty bit. It works great. On a Delta, however, the end of the Delta moves around very quickly, and you want as little mass on here as possible. And so in a Delta, the extruder is actually up here. And what that means is the extruder has to push plastic all the way through this long tube here, called a Bowden tube, down into the printhead. When you're doing travels between different parts of an object, you'd usually try and retract the plastic up, try and suck it out of the printhead and stop it oozing. In a direct drive, this is pretty successful. The drive is so close, it just sucks plastic up and it stays in the right place. In a Bowden, however, you've got 40 or so centimeters here of plastic in this tube. And so whenever you try and retract, you're going to find yourself dealing with the elasticity of the plastic as you try and put it up through that tube. What this means is retraction is much, much harder to get perfect on a Bowden-style extruder like this. Now, faced with this problem, I of course did one thing, and that one thing was buy a new 3D printer. This, the Cetus 3D. The Cetus is a low-cost printer. It's only $300, and it's a little bit bare bones, but it has these lovely linear bearings for each of the axles and has very good reviews about how well it performs. And so I made the plunge and got one. And I've been very impressed. I got the Cetus, plugged it in, turned it on, sent it one of my files to print and slice, and it just printed it. The result is, as far as I can tell, pretty much perfectly square. There's no stringing at all. The details and the towers look really lovely. And so the Cetus has become the workhorse for this project. The combination of our Cartesian style of movement combined with the direct drive extruder means it has that square accuracy and the lack of oozing that I'm looking for. There are some drawbacks. I have three main kinds of plastic I 3D print with: PLA, ABS and nylon in increasing order of durability, and the Cetus can only really do PLA. The lack of a heated bed means that it's very hard to make ABS print well on this machine. The Rostock has a nice heated bed, you can make an enclosure around this and do ABS and nylon very well, but this is just PLA. That said, I like using PLA. It's easy to use, it melts very effectively, and doesn't emit any sort of toxic particulates while it's printing, and so that's what I've chosen to make my 3D models out of. The one downside to PLA for this project is that it will melt in bright sunlight. If it gets above 50 or so Celsius, it starts going slightly oozy and melty. But as long as I keep my things out of sunlight and away from any hot areas, they should survive quite a decent amount of time. It's also biodegradable, which is always nice. Now I've talked about the different kinds of printers, let's go and look through how we send data to them to print. In particular, slicing a model and sending it as G-code to the printers. The Cetus has its own built-in software for this, whereas the Rostock you can use several pieces of existing software. I'll show you around both to give you an idea of what sort of thing is involved and the settings you want to tweak for things like retraction and oozing on a printer like the Rostock. First off, let's look at Matter Control. Matter Control is the software recommended by the manufacturers of the Rostock, CME-CNC, and the one I use for most of my prints on that machine. It's got a reasonably simple interface. Over here on the left is a queue of objects to print. I've picked a small egg cup here as the demonstration model because loading the city tiles into this program makes it slow down a lot, and trying to record and show you this stuff would be problematic. So we've got the egg cup, and then we've got two views, this 3D view here, and then the second one, the layer view. The layer view shows you the actual tool path the printhead will take and the layers it's going to make for the model. You can see here the very base of the egg cup is just a couple of layers onto the print bed, but as you go further up, more and more detail starts to emerge and the different layers appear. The colours are the speed of the printhead. As the printhead has smaller and smaller pieces, it has to slow down to make sure the plastic has time to cool before the next layer. Otherwise, it will just go back over a hot melted plastic and just ruin the previous layer. But you can see here the final egg cup and all the layers that would go into making it. Now, of course, you don't just put things into the program straight away. There are options of how you slice it. And the main two options here are two presets. The quality, which generally determines the speed and layer size, and the material, which determines the temperatures the printhead uses to melt the plastic. Here I have coarse and PLA hot selected. The core setting sets the layer height to a 0.3 millimeter. That makes the layers fatter. So you do less layers, but you'll see more obvious ridges on the part because the layers are much more visible. It also turns the speed up above the recommended basic limits for the printer. The delta can go pretty fast, but it will start to lose a little bit of accuracy the faster you go. The PLA hot setting is just PLA settings turn up a little bit in terms of temperature. You can see here in the filaments, the extruder temperature is 190 and the bed temperature is 60. There's options here for other things such as PLA, ABS, and even flexible rubber-like filaments like NinjaFlex. There's also other options to how it's sliced. We can see here lots of things about, for example, how high the layers should be, how many perimeters we should do. If we look at the two-dimensional view and go to the middle of the egg cup, you can see that there's only 2 or 3 perimeters used anyway. And so it's not going to make much of a difference. We could, if we wanted to, turn this down to 2 or 1 perimeters. Let's put 1 in here and regenerate. Now, we've regenerated with only 1 perimeter, and going through the model, you can see that the inside is much more hollow. There is a little bit of infill, but that is in the empty area. There's some lines and cross-hatching here, which is controlled by our infill setting. We can change the pattern of that kind of stuff as well. But generally, it's a case of going through here and finding out what works exactly for you. The city tiles in particular require a lot of attention to things like the retraction settings. Here in matter control, those are under filament. And you can see here a couple of options around how those are changed. The most important setting here is the length of retraction. This is how much the extruder motor is going to pull that plastic back out of the printhead while it tries to move the printhead through space. Now, here it's set to 4. This is quite high, but about right for the Rostock. But for a smaller printer like the direct drive on the Cetus, probably more like 1 or 2 millimeters at most. My recommendation for the Rostock is about what you see here. No Z lift, a decent amount of retraction, and going at quite a decent speed. There's many other options in here to play with around as well. Things like the temperatures, the way the fans go for cooling. PLA requires cooling as it's printed to make sure the previous layer is set in time for the next layer. And plenty of other things about how the supports work or having a raft to keep it on the bed. But these are topics much better covered by other people. This is just a general idea of what you end up with when you take a 3D model, like this egg cup, and pass it through a slicer like this to get the resulting toolpaths. The final step is to take these toolpaths and export them as G-code. What we can do here is just select the model, hit export as G-code. And then we can just save these into the right place, and we have a G-code file we can send to the printer. In the case of the Rostock, the printer takes either an SD card with G-code on it, or you can connect something like a Raspberry Pi running Octoprint to it and send files to that over web interface. Let's go over to the Cetus interface now and see how that looks. So here you can see the Cetus interface. It's an all-in-one program that does printer communication and slicing in one go, but handily it can talk to them over Wi-Fi. So we can go in here, select my printer, and connect to it over Wi-Fi. Once we've done that, we can go to the print screen and do a couple of things. First of all, we can add one of the models to the print area. The box on the screen here shows the entire build volume of the Cetus, that is where it can print. And so if we go in here and just pick one of these models, these are the London tiles in this case, it will load up the model and we can see it here rendered on screen. Now, notably, the Cetus software is remarkably good at slicing large, complex things like this very quickly. On things like matter control or slicer, this will take a good 10 minutes to slice properly. Whereas here on the Cetus, we can just hit the print button, choose some of our options. We have, again, layer thickness and the infill patterns and how you want to infill, as well as some more advanced options as well over here. But you can just pick these options, hit preview in this case, and it will slice in less than a minute, which is a very impressive performance for something this complicated. These models generally have on the order of 30 to 100,000 polygons in them, so it often chokes up some software. So here you can see it's finished slicing. It's giving me an estimate of both the print time and the amount of material it will take to print. You can also see here that it's made a raft underneath the object. This is one small thing about the Cetus. It likes making a raft to keep the print adhered to the print bed. It does waste a bit of plastic. On something this big, it's a good 30 grams of plastic just to make the raft. But I have seen very good results with the raft, keeping the bottom of the tile lovely and clean and making sure it peels off really nicely. Now, unfortunately, I haven't found an easy way to view the layers in the Cetus software, but that's not a problem. It generally does a pretty good job of slicing it anyway. So once you've got the model loaded in, you're happy with the way it looks and the arrangement on the print bed, you just hit this button here to initialize the printer and home it on all 3 axes. And once that's done, you can just hit print, make sure your options are still good, and send it over to the printer to be printed. The CSys runs everything by itself, so once it's sent over, you can just close the software and let it run entirely disconnected from a computer, and it will happily print away until it's completed. This is especially useful for these big city tiles where they might take 10 hours to print. I want to make sure they print overnight without leaving a computer on or plugging in a Raspberry Pi to act as the brains of the operation. So that's the basics of slicing. Once you've got the STLs like you saw in the last piece, it's really not too hard to put them into the software of choice and make them come through. You might have to fiddle with some options to make sure they print perfectly, things like the infill patterns or retraction, but I recommend printing small test pieces, say a 1/8 size piece of tiles like this, and making sure they turn out well before you start on the big tiles and the long, multiple hour prints. Well, that covers slicing the STL files into G-code and sending them to the printer. Now, there's one thing left to do, and that's assemble them into one big piece of art. So let's go back to the table and start on that process. The final part of the process is to take the printed tiles, finish them off, and then mount them onto a backing board. Finishing them is pretty simple. I just need to make sure that the edges of the tiles are perfectly smooth so that when they jot together, the edge between them is almost invisible. For this, I just use a piece of sandpaper like this, glued to a nice flat block of wood to sand it down. PLA is very easily sandable. Once that's done, I need to mount them onto a backing board. Now, there's a couple of options of what to mount to, plastic or wood. I've gone in this case with foam core. Foam core is light and inexpensive and easy to cut with scissors or knives, and so it's a good choice for this kind of project. What I'll be using to mount to the backing board is hot glue. Hot glue is also nice because you get a little bit of working time as the glue sets to really get the tiles in just the right place and make sure they're perfectly flush with each other. And if I screw it up, I always have the choice of ripping them off the backing board. The glue is not that sticky. It'll probably destroy the foam core, but it's cheap enough I can get a new piece. So let's get to it. Well, that was a bit trickier than I expected to glue them all down precisely, but it's done. And I've got to say it looks really quite nice. The hills and the buildings stand out really well, and some of the problems I had in the London model, like very visible seaming between tiles, are almost entirely gone here. There's a small seam, but it's quite hard to see, and at any sort of angle it vanishes entirely. There's a couple of things left to do, the main one being to glue some wood along the back here to act as a place to hang it up, but I'll do that later. And with that, we've reached the end of the build. I hope you've enjoyed watching and learning about this as much as I have making it, and don't worry, there's more to come. Not only am I going to redo my London map in the same style and process, but I have another secret project involving national parks and milling machines, as well as some other side projects I'm working on. But until then, I'll see you around.